Now we want to learn a little bit more about what's called u-substitution. So when we're talking about this section 5.5 and u-substitution, what we're talking about is integrating problems where the chain rule was invoked. So these are problems where we had composition in a function. So we had f of g of x. Remember, when we take the derivative of f of g of x, we get the derivative of the outside, freeze the inside, multiplied by the derivative of the inside. So hopefully this reminds you of sort of what we did there. So let me give you an example using the chain rule so that you can remember what it looks like. So let's say you want to take the derivative with respect to x of the square root of, we'll make it simple, sine of x. So I have two functions going on. The square root is one function and sine of x is the second function. And I have a function inside of a function. This is composition. So when I do the derivative of this, remember I take the derivative of the outside, which the last thing to be done would be the square root. So the last thing in order of operations is the outside function. So I take the derivative of the square root, and remember we've memorized that the derivative of a square root is 1 over 2 the square root. Now we freeze the inside, we leave it sine, so we freeze the inside, and then we multiply that by the derivative with respect to x of the inside. So then this is called the chain rule, f prime g, g prime of x. So this gives us f prime, derivative of the square root, with g, sine of x still plugged in, times g prime of x. Now, derivative of sine is cosine. So when we were finally writing the solution, we would have cosine of x over 2 to the square root of sine of x. This is what the derivative form looks like. Now, we have to go backwards. We have been teaching you how to do something and then how to undo it. So the primary thing we taught you this semester to do first was in chapter 3, we taught you to take derivatives. And now in chapter 5, we're teaching you to undo the derivatives with the antiderivatives. So what if you got something like this inside of an integral? You have to be able to come up with the original function, which is over here, the antiderivative. So we have to be able to look at something like this and pull it apart and undo the derivative that was done on it. This is probably, if you want to think in terms of importance in the course, section 5.3, the fundamental theorem of calculus, is the most important section in the course. Very, very close second is this section. This is the second most important section in the course. You'll want to spend a lot of time here because u-substitution will be almost as common as doing the fundamental theorem of calculus part 2. So when we're looking at this, we're going to have to learn how to apply this u-substitution in reverse. All right. In order to apply a u-substitution to an integrand, the integrand needs to have the form of f of g of x, g prime of x. In other words, it needs to have the form of the result of the derivative. So that would be this thing right here. In order to do that, then, we're going to maybe have some constant multiple that's not present or that's present and shouldn't be. But constant multiples, remember, can always be pulled outside the integrand. So we won't worry if the constant multiple isn't correct, but otherwise it's got to be basically that form. All right. And this should be f prime. I don't know why my prime's not there. All right. We should have f prime of g of x, g prime of x. This is called u-substitution because we're going to substitute part of the integrand with the variable u. And then we're going to set up a relationship between u and the original variable, whether it's x or t. And we're going to take the derivative of both sides. And we're going to get a du dx. And then we're going to abuse the notation. Yes, I did say abuse. We're going to abuse the notation so that we can get dx in terms of du. And we're going to substitute for the original differential in terms of du. This is also called a change of variables because we're switching from an integral in terms of x or t into an integral in terms of u. And there are occasions where this has to be done more than once in a problem. And in that case, we'll switch it from u, and then we usually go to omega, which looks like a w. All right, okay. So we're going to start here with our function. We have f of g of x, g prime of x, equal to this expression over here on the right-hand side. And that's going to give us what we need. Now let's go through the proof of this. The proof says, let u be g of x, where g prime of x is continuous over an interval, and let f of x be continuous over the range of g. In other words, you put x into g, and g spits out y values, lots of y values hanging around. Now, f applies to the y values, and it's continuous over those y values. Let uppercase f of x be an antiderivative of lowercase f of x. Then applying the chain rule to uppercase f of x, f of g of x, we have chain rule f prime of g of x times g prime of x, which gives us f of g of x, g prime of x by assumption. So this is the original function applied to g of x times g prime of x. Then we're going to integrate both sides of the last equation where we have the derivative of uppercase f on the left, and we have lowercase f of g of x times g prime of x on the right. So we integrate the two sides. Now remember that the integral and the derivative with respect to the same variable are inverse operations. And so they essentially undo each other. So what's going to happen then is we're just going to get f of g of x plus some constant of integration equal to f lowercase integral f of g of x, g prime of x. Now we're going to substitute for the composed function. We have a function inside of a function. G of x is inside of f. So we're going to substitute for the inside function. So when we're doing u-substitution, we're going to look for what's on the outside, and we're going to look for what's on the inside. And we're going to choose the inside function to be our u. Sometimes there's more than one possible choice of u, and it becomes sort of trial and error. But trial and error guided by having done lots of problems, which develops intuition as to which one is most likely to work. All right. So then we compute the derivative of u with respect to x. This du equal to g prime of x dx actually started as du dx equal to g prime of x. Now, how did that happen? Well, you had u, and it was equal to g of x. And they take the derivative with respect to x of both sides. That's going to give you du dx equal g prime of x. Now we abuse the notation. And yes, that is what it's called. It's an abuse of notation. Why is it an abuse of notation? Well, this d by dx represents the derivative operation. It is not a fraction. I know it looks like a fraction. It is not a fraction. It is the derivative operation. But, and here's the genius of Gottfried Leibniz's notation, if we treat it like a fraction, it works, and it always works. So we abuse it and treat it not like a derivative operation, but as if it were a fraction. and we take the dx and we multiply it to the other side of the equation. This is called an abuse of notation. So we separate the du from the dx, which is definitely an abuse of notation. The whole thing is one operation. I shouldn't be allowed to do it, except that it works. Now, once I have them separated, if I want, I can solve for dx by dividing by g prime of x. And that will let me substitute in the original integral in place of dx. Looking down here, what we see is this becomes f of u du. So right here, you can see where we've solved for du, which is equal to g prime of x dx. And so we substitute in place of g prime of x dx, we substitute du, and in place of g of x, we substitute u. So now we have this integrand function, and we know that the integral of f of u becomes its antiderivative function, uppercase f, at u, which becomes f of g of x plus c by substitution. And that's a proof of the operation. Now that's all well and good, but it doesn't really tell you how to do u-substitution, does it? It's a proof of the theorem, but it doesn't tell you what you're actually going to do. So here are the steps that you want to go through for u-substitution, and these are guidelines. These are not hard and fast rules, because again, there are sometimes more than one possible choice for u. So these are guidelines on how to find u. You're going to look carefully at the integrand, and you're going to select an expression, which is generally the inside function of a composition. So you're going to look for a function within a function, something under a radical, something in the power of an exponential, the base of something being raised to a number power, an expression inside of a natural log, an expression inside of a trig function. You're looking for a function inside something else. You're going to set the inside function to be u. You're going to make sure when you pick that u, that at least part of its derivative is also in the integrand already. So if your integrand is, I don't know, let me come up with one so that we can actually practice this as we go through. Let's say e to the x cubed plus 4. All right, where's my inside function? Where's my outside function? I have a function x squared, but it's not inside anything. It's being multiplied by an exponential. The exponential itself is a function, e to a power. In the power, I have another function, x cubed plus 4. Bingo. I have a function inside of a function. I'm going to choose my x cubed plus 4 to be u. So I choose u to be this power that's inside the exponential. But when I do this, I want to make sure that at least part of the derivative of u is already inside the integrand. So I'm going to take the derivative of u with respect to x, and I get 3x squared. Now, when I say a part of it, what I really mean is a multiple of it. It has to be in there except for the multiple, the constant coefficient. The derivative of u is 3x squared. The 3 may or may not be in there, but the x squared had better be. And when I look at the integrand, I can see that x squared is in the integrand being multiplied by the exponential. That's what I'm talking about. The constant multiple may or may not be there. It may be the wrong constant multiple. That's okay. We won't worry about the constant multiple. But the variable part of the derivative must be a part of the integrand, or we've chosen the wrong u. Then I'm going to make a substitution for u, so that I'm going to rewrite this as e to the u. Now I have to make a substitution for the rest of it as well. Now, in some textbooks, they emphasize substituting for du. We're actually going to do something a little bit different. We're going to abuse the notation that you see right here, and we're going to swing the dx to the other side so that we get du equals 3x squared dx. And then we're going to solve this for dx. Dx equals 3u over du over 3x squared. Does everybody follow what I did? I took the derivative of u with respect to x. Then I abused the notation and split up the du and dx. And then I solved for dx by dividing by 3x squared. Now I'm going to substitute for the differential dx. What's still in the problem is this x squared. It's still there. And then I'm going to have du over 3x squared, which replaces dx. Right? So I replace the power with u and get e to the u. The x squared is still in the integrand. And I replace dx with du over 3x squared. What happens to those x squareds? What happens to them?
They're gone.
They're gone. They cancel. They become a 1. So this will give me the integral of e to the u du with a 1/3 coefficient that I can pull to the outside of the integral. Now, can I integrate the integral of e to the u du? Yes, I can, right? I can definitely integrate e to the u du. The derivative differential is du, which indicates the variable is u. So e to a power, the antiderivative is still e to the power. We should now be able to evaluate the integral with respect to u. If you can't, you've chosen the wrong u, go back to the beginning and start over. So this becomes 1/3 e to the u plus c. Now, we have to remember that the original integral was written in terms of the differential dx. Because the original is in terms of x, we want to go back to that original variable. So we're going to back substitute for what u was. We set u to be x cubed plus 4 right here. And so then we back substitute and write 1/3 e to the x cubed plus 4 plus a constant. Right? These are the steps that we go through to do a u-substitution problem. We're dealing with composition of functions and undoing the chain rule in essence. All right? We will not learn this semester how to undo the product rule or the quotient rule. I know that sounds crazy. We learned product rule and quotient rule before we learned the chain rule. But product rule and quotient rule, it turns out, are far more difficult to undo than the chain rule, believe it or not. In fact, we need multiple techniques in order to undo products and quotients. In fact, when we were looking at the integral table over here, you'll find that many of the ones down here, as you go lower and lower in the numbers, deal with products and quotients of different types. Now, I don't know exactly what number we're up to. When I was a freshman in college, the number of known integrals was around 1,200 patterns. Yes, 1,200. 1,200. I believe we're now upwards of 1,800, if I'm not mistaken. So there are books of integrals which deal with products and quotients. So they're not simple to undo at all. Let's take a look at example 1 now. We want to look at example 1, which is going to integrate the sine to the 10th of theta, cosine theta, d theta. Now, we typically do write the integral with the sine and the 10th power being between the sine and the angle theta. But it could also be written in this format: sine of theta raised to the 10th power cosine theta d theta. Now, this makes it a little bit more clear in the second form that the inside function is sine and the outside function is raising to the 10th power. So we have composition right here in our integrand. We also have a part being multiplied, as it must be, that is not a part of the composition, but it should be part of the derivative of u. So our obvious choice to choose for u would be sine of theta. It's inside being raised to the 10th power. So we're going to choose u to be sine of theta. And then we're going to find du by taking the derivative with respect to theta of both sides. Why theta? Because the original differential is theta. And it tells you what to take the derivative with respect to. So we take the derivative with respect to theta of u and the sine of theta, because we set u to be sine theta. Then we take the derivative of both sides, which gives du d theta equals cosine of theta. Now we abuse the notation. Yes, it's called an abuse of notation, to swing the d theta from the denominator over to the other side. I hate to even call it a denominator because it's not a fraction, technically. This gives us du equals cosine theta d theta. The easiest thing to do is then rewrite this as d theta equals du divided by cosine of theta. And now we substitute for each individual part. Instead of having sine of theta to the 10th power cosine theta d theta, we substitute u to the 10th power, cosine of theta is still there, and we replace d theta with du divided by the cosine of theta. Now the cosines of theta will cancel out, and this gives us the integral of u to the 10th du, which just invokes power rule. So when we apply the power rule, we get u to the 11th divided by 11 plus a constant. This is an indefinite integral, so we're looking for an antiderivative function. We go back to the very beginning equation to see what the original differential was, and we return to that variable d theta. So now we're going to take the u to the 11th over 11, and we're going to substitute out u and rewrite sine theta. Now this can also be written in the format sine theta to the 11th power divided by 11 plus a constant. Either one of those is correct, right? Let's do one more problem. This is an exponential, much like the first exponential that we did. This is e to the 3x plus 1 dx. We have an exponential and we have the function 3x plus 1. The function 3x plus 1 is inside the exponential. So we're going to let u be 3x plus 1. Oops, I have a typo. How did I miss that? I thought I had fixed this. Okay. This is supposed to be no theta there. I don't know how theta got crept in there, but it should be dx. So we have u, the original differential was dx. So we take the derivative of u with respect to x and the derivative with respect to x of 3x plus 1, which gives us du dx equals 3. The next thing we're going to do is abuse the notation and swing the dx around. So this gives us du equals 3dx. Finally, we solve for dx in terms of du, and we get dx is du over 3. Then we take the integral e to the 3x plus 1 dx, and we substitute e to the u, and instead of dx, I write du over 3. Now the 3 is a constant, which means it can come out front as 1/3, and I get 1/3 the integral of e to the u du. Now the integral of e to the u du can be integrated directly. It gives us the antiderivative function e to the u times the 1/3 plus c. And finally, we want to return to the original variable. So we scroll up and we look at the original variable and we see it was originally dx in the differential. So we replace u with its equivalent value, 3x plus 1, and we get the antiderivative function, 1/3 e to the 3x plus 1 plus c. In the next video, we'll look at lots of examples of u-substitution. Then we'll take a look at u-substitution in definite integrals.